Thank you very much. It's a pleasure to have been invited here to talk to all of you today. I came to Lawrence Livermore 7 years ago, but I'm going to be talking to you about the work of well over 1,000 people, well over 1,000 scientists and engineers who have been working on the pursuit of sort of the frontiers of laser energy and laser power for the pursuit of fusion. That is controlled nuclear fusion in the laboratory setting, and hopefully with a dream of clean, sustainable power. In contrast to our previous speaker, who was talking about the small, the random, the oscillator, I'm going to be talking about the large, the deterministic, and the amplifier. So within the laser community, we sort of say the term laser, but we often talk sometimes about oscillators, which are sources of light, which require feedback and amplification. I'm going to be talking to you about the amplifiers, which then take an oscillator and then ramp it up to very high energies and very high powers. So first I'm going to give you a brief introduction to Lawrence Livermore National Lab, which is another Department of Energy lab, much like this one, located in the Bay Area. Perhaps many of you have already been out there for conferences or vacation. San Francisco and Silicon Valley are roughly 1 hour to the west, and then the Sierra Nevada, Lake Tahoe, Yosemite are about 3 hours to the east. The lab itself is about 1 square mile, located in a residential area. And many of the recent research and development projects have been focused on high energy and high power lasers. In fact, lasers are scattered throughout the lab. There's an old joke at Lawrence Livermore such that the acronym LLNL really stands for lasers, lasers, nothing but lasers. So here we have some of the early laser facilities that were built are all kind of clustered in the Jupiter Laser Facility, which has become sort of a user facility for students, postdocs, and small-scale experiments that need to be tested before they're fielded on the larger scale systems, which are more costly to run. We have the Nova laser, which was sort of the workhorse in the 80s and early 90s, and toward the end of its run was upgraded to demonstrate the first petawatt class laser, the highest peak power. And that still holds the record. Since then, Nova was decommissioned, and the National Ignition Facility was designed in the mid-90s. Construction began in the very late 90s, and we just completed the laser last year. So I'll be talking mostly about this, which is now the world's largest and most energetic laser. Similar to the Nova upgrade, we're also going to be talking about an upgrade that will take NIF and add advanced radiographic capability, which will take us to many petawatts of peak power. Then I'm also going to be talking about the next frontiers, which involves scaling up not only the energies and the powers, but the average powers. That is, to be able to run these machines not on a single-shot basis, but rather on a multi-shot basis. And if we can do that, then there's some chance that we can actually build a power plant based on these systems. So Mercury has been a prototype laser that has been operational for about a decade now, trying to achieve this goal of demonstrating on a very scalable architecture how we can run these lasers at greater than 10 hertz. And then LIFE is a concept we have right now for a 10 megawatt laser fusion power plant prototype, and I'll show you how that works. Okay, so as an outline, I'm going to review the current frontiers of laser energy and power, talk about how you scale up to megajoules, both at NIF, and talk about, within NIF, how we achieve flexibility in tweaking the conditions required for laser fusion, and how over the last few decades the size and purity of optics have been increased and developed to the point where we can sustain very high fluences without laser damage. Then I'm going to talk about peak power scaling to petawatts. I already mentioned the arc laser. Then average power scaling to megawatts. And then I'm going to talk about the next frontiers in laser performance required for clean, sustainable power generation. So very briefly, here's a couple of cartoons which sort of demonstrate what these three performance parameters are that characterize lasers. The first is energy. So you can think of this as a pulse of light, and the area under the curve, sort of the peak power multiplied by the pulse width, will give you the energy content. So the NIF laser is targeted at 1.8 megajoules in the ultraviolet. Right now we've shot 1.2, and we're ramping up to this over the next year. This is about 30 times, or more than 30 times, any previous laser that's been constructed, any system. The main problem here is avoiding thermal damage on the optics, particularly at the end of the amplifier and in the lenses that are used to focus the light at the very end. On a peak power basis, it's all about taking this energy and compressing it to a very short pulse width. So there's been many almost tabletop systems that have achieved tens to hundreds of terawatts across many academic institutions. And these have all been done at very modest energies, but with the pursuit of very high peak powers. The Nova laser back in '96 achieved 1.25 petawatts. Most recently, the Texas petawatt is currently the world's most powerful laser. And we're working on an upgrade to NIF that will take us beyond that. And there the main problems are ablation damage, self-focusing, that is, the beam of light is powerful enough that it creates its own lenslets and it collapses at filaments, both on the whole beam scale and on the small scale. Finally, there's average power, and this is a grand engineering challenge. How can you operate these lasers at high rep rates and avoid thermal lensing, rupture, melting? Sort of the largest average power or highest average power lasers to date are all run for military purposes, the Boeing airborne laser. And if we can build this power plant, we would have about a 60 megawatt class laser for fusion. So in comparison, 15 terawatts is about the average consumption of power in the world. So back in '62, only 2 years after the demonstration of the laser, it was quickly recognized that lasers could be used to achieve fusion in a controlled fashion. The energy threshold, though, is in the megajoules. And for building these systems, really everything becomes non-trivial. So in our field, we typically require spatial filters to make light very coherent. And these spatial filters consist of pinholes that you pass a focused beam of light through and then clean up light at higher frequencies. Well, those pinholes, even if you have a little bit of light in the wings of your beam, will vaporize. Or they will create a plasma that will then close off the transmission. So you have to avoid that. Optics require near-perfect finishing, very low defect densities. You have to register your beams because if you're off by just a little bit, you will completely spall the metal on the mount that's holding the optic. So those are some of the challenges in scaling up to megajoules. And then to achieve the conditions required for fusion ignition, that is to actually take deuterium-tritium fuel and actually getting the densities and temperatures up to the point where they can actually initiate a fusion reaction, really requires a number of things involving power balance, precision pointing, synchronization of both beams and pulses. And when you're all done, you really need to be able to resolve the data so you know what the laser is doing. So diagnostics require something that you just simply can't buy off the shelf. And then achieving the conditions required for a power plant will then require high rep rate, target tracking, low-cost semiconductor pump diodes is a big one. The economics of bringing the cost down on these pump diodes is going to be huge in the next decade. And, of course, reliability. So here's NIF. And NIF is really sort of the culmination of a long line of high-energy lasers built for fusion research, going back to the early 70s of the Janus laser, which was just about 100 joules in the IR. Then Shiva, Nova, Omega at Rochester scaled this up. There was a switch from operating at 1 Omega in the IR to 3 Omega in the ultraviolet, and that is for greater X-ray efficiency. So this is what the stadium looks like. You can fit 3 football fields here, one here, another here, and a third one there. The laser is really housed in this facility. There's an optics assembly building over here, and the target chamber where all the lasers converge is over in this building here. So this large-scale facility takes 192 laser beams and focuses them down to a pellet about the size of 100 microns. And that pellet is surrounded by a gold cylinder. The gold cylinder takes that optical energy, converts it temporarily into a black body X-ray oven, which then allows you to, in a very symmetrical fashion, compress this pellet. Plasma physics is not my field, but here are some very daunting numbers. We're trying to achieve matter temperatures of about 10 to the 8th Kelvin, radiation temperatures a little bit less, densities that are 1,000 times out of water, and pressures that are 10 to the 11th atmospheres. So essentially we're trying to create the conditions at the core of the sun so that we can initiate these fusion reactions. So this is what the inside of the target chamber looks like. This is a 10-meter ball of aluminum. It's about 1 million pounds. And there are multiple ports in here. The square ports are where the beams come in, and there's 4 per each port, arranged in quads. Circular ports are mostly used for diagnostics. And then here we have a target holder here, so that the target is actually located at the end of this point. And then we have a camera system here, which is used to peek back at all the optics and make sure that they're not being damaged. Okay, so here's a cartoon schematic of the final focusing optics. So these are 40 centimeter by 40 centimeter optics arranged in these quads, like I mentioned. And within each of, this is all a line replaceable unit. That is, if something fails there, the entire thing is taken offline and replaced with a new one. But within each of these quads, we have a number of optics in series. So there's phase plates, there's windows to hold off the vacuum in the chamber. There's polarization rotators for smoothing. When you interfere these beams, you want them to interfere in a very smooth fashion. And you don't want speckle. Speckle is a phenomenon that you get when you have this coherent interaction of all these beams. So for many reasons, you want coherent light. For this particular reason, we want to spoil it. Then we have frequency doubling and tripling crystals. These are some of the largest crystals, nonlinear crystals ever made. And then we have our focusing lens, which is wedged. You can think of it as a piece of a spherical lens that's been cut off-center. And that's so that we can have a separation of the 1 omega, 2 omega, and 3 omega light. And there's some light that doesn't get converted in these crystals, and that ends up being focused and lost. But we really care about the 3 omega. Then there's debris shields and other diagnostic type optics there. If you look at the sort of the parameter space of NIF, we'll be operating in a regime that's roughly 7.5 times larger in total beam area and about as much as a factor of 12 larger in terms of operating fluence. So fluence is energy divided per area. And it's fluence that really governs just how these surfaces damage and how that damage evolves over time. So here you can see the scale up of the laser glass. So this is the gain media that Livermore has been focused on. It's neodymium doped phosphate glass. And it has a number of attractive properties, mainly because you can scale it up to large apertures and continuous melts, but also it has very nice properties in terms of its saturation fluence and its damage fluence. You always want to operate an amplifier such that its saturation fluence, that is, where you can fully extract all the energy and maintain a very stable output, you want that to be less than the damage fluence. Many materials don't behave that way and will damage before you saturate. So improving the surface finish of the fused silica optics that are used, say, in the wedge focus lens has been a primary concern. And there's been a lot of tremendous development from '97 to the present in terms of bringing down the number of damage initiations per square centimeter way down from, say, 10 down to almost 10 to the minus 4 now. What happens is you have an initial site, which may be an impurity on the surface of a lens, a defect, a dig, and that may be only tens of microns, but with every subsequent laser shot, you have deposition of heat at that site that will grow to the point where it can grow uncontrollably. And it can cause fratricide, too. It can create a perturbation on the beam, which then focuses that beam, creates a hot spot on the next optic, and then takes that optic out. So as a result, we have this camera system that after every shot, and imagine that every shot requires about a 3-hour cooling period, and reset up in realignment. We insert this camera and we peek back through all 192 beam lines and scan every interface on every optic. We track that data automatically, and then we look for new sites that have developed, and we look and see whether or not they've grown in cross-section. So recently we upgraded the front end to be able to be adaptable. That is, back in the low fluence part of the system, where the beam is only a few centimeters and only a few joules, we shape the beam using a spatial light modulator. And this just shows the demonstration of our ability to actually put complicated shapes on the beam. But what we really care about is being able to put these blockers on there. Locally, put a dot on the beam, a shadow, so that downstream that shadow is imaged. If we can register that with a defect, then we can effectively keep the energy up high, but locally keep the energy low so that we don't damage. So we've engineered this system, we've just deployed it, and we're bringing up the software so that we can, in a very automated fashion, continue to run NIF without having to replace these very costly final optics assemblies frequently. Now I'm going to focus a little bit on the target. So here, if you zoom in there, Here's what a target looks like, and it's housed inside this gold cylinder, which in and of itself is a mechanical engineering marvel. There's a point designed for the ignition capsule here, which has an ablation layer. So that is when the X-rays strike the ablation layer, they blow off, and due to Newton's law, you have an equal and opposite force that crushes the fuel inside in a radial fashion. But as you might imagine, if you've ever tried to squish a balloon, symmetrically from all dimensions, it's not an easy thing to do. So imagine trying to squish, say, a basketball by a factor of 40,000, and doing so in a very symmetrical fashion. That requires very careful precision of the alignment of your beams and adaptability. If there's perturbations, in the surface structure and morphology of the target itself, you want to be able to adapt to those by tweaking the laser parameters. So at a very high level, there's a number of parameters that the plasma physicists need to ask of us laser engineers to be able to deliver so that they can effectively tweak all the knobs on NIF so that they can actually achieve fusion. One of the major challenges is to design this carefully crafted pulse. So here, this pulse that you see is really about the pulse that we shoot. There's multiple features here. You see that there's 3 sub-pulses, and then there's the main pulse. These sub-pulses are carefully crafted to strike the target at specific times and resonate with it, much like kicking or pushing a child on a swing. You want to be able to push that child at the right time so that you can resonate and create a shock that propagates to the center of the target and really reduces the overall energy threshold that you need. So the energy threshold is something that's limited by the amplifiers and damage, but we still have the ability to tweak the pulse shape at the front end, and then that front end, that weak energy pulse will be faithfully transmitted, of course with some pulse distortion that we pre-compensate for, but you'll effectively get that pulse shape at the very end. And then there's a number of other parameters, but I'm going to move on in the interest of time. This just shows our ability to create that pulse. So here's the designer pulse that the theorists gave us, and then that's sort of the experimentally measured traces that were recorded up to 1.2 megajoules. Now I'm going to switch topics from energy to peak power. So this is sort of the technical breakthroughs that have occurred ever since the invention of the laser in terms of achieving very high peak powers. In the early days, we just ran lasers in a free-running mode. We charged up a flash lamp, discharged it, and the storage time of the gain media dictated the pulse width that came out. Then Q-switching came along, in which we held off a laser's amplification until the moment we were able to open up a shutter and let that come out very fast. Then mode locking, and then chirp pulse amplification was an invention at Rochester that was first successfully demonstrated at Livermore to achieve a petawatt. And that really works by taking a short pulse in time, stretching it, and we stretch it by separating the color content of that pulse in time. We call it chirped because, much like in audio frequencies, you have a change in frequency as a function of time, much like a bird chirping. But if you can stretch this out, then you can amplify this safely, and then only at the very end of the system compress it again to very high peak powers. So if you can do that, then you can avoid ablation damage, self-focusing, filamentation, other problems with very high peak intensities. So why are we doing this on NIF again? Well, the main thrust for now is to create a frame-by-frame X-ray movie of what's going on when we're imploding this target. So we're going to dedicate, of the 192 beams, we're going to keep 188 as is, and we're going to dedicate 4 of them to strike metal foils and serve as backlighters. So these backlighters work by taking a laser pulse, striking a foil, that creates X-rays, and you really need high intensities to create 100 keV X-rays that are required to actually penetrate the high densities of this imploding target. Additionally, you want the pulse short so you can resolve the features that are occurring across sort of a 10 picosecond resolution timescale. So these 4 beam lines are actually going to be subdivided into 2, and we're going to have 8 pulses that come out, so we'll have an 8-frame movie when this is all upgraded. This is something that we should have up and running sort of in the 2011, 2012 timeframe. These are sort of the modifications that are being done in parallel as we're operating the facility. I won't go into the details right now, but essentially we're working towards having 8 individual petawatt beam lines. This is what the the NIF target chamber looks like. This is the surrounding infrastructure. This is one of the beam paths here. So there's 4 beams that come down, and they're routed by mirrors in a switch yard here. And we're going to modify that particular quad by redirecting some of those beams into 2 vessels that contain grating compressors. I don't know if you're familiar with diffraction gratings. If you've ever looked at the surface of a CD or a DVD, you see a rainbow pattern coming off it, and that's because of the very fine grooves that are diffracting light in a resonant manner into various angles. So if you can play this game with a short pulse, stretch it out into its various colors, at the very end you still need to compress it. And the way that you do that is you let the red parts of the pulse, or the longer wavelengths, travel a shorter distance than the blue, and then you can make all the colors arrive at the same time. So we developed a facility starting back in the late 90s to develop the largest diffraction gratings in the world specifically to achieve this purpose. Next, I'm going to finish up with some of the breakthroughs that are required to take these single-shot lasers and run them at rep rate. So the Mercury Laser, as I mentioned before, is a prototype that's been pursuing this goal for the last decade. And they've made a number of interesting contributions to the field. They've really pushed the development of 100 kilowatt class diode arrays, so very massively parallel arranged packages that are thermally cooled to be able to run these continuously. Then they have a front end which is very adaptable. They're developing new gain media that is very efficient. So to run at rep rate, you need a media that's efficient for 2 reasons. One, you want to extract all the energy. But 2, most of the energy that you don't extract is usually left behind as heat. And that can become a problem. How do you extract that? So it's sort of a double whammy. Pockle cells. So a Pockle cell is sort of your classic optical switch that can operate at the nanosecond time scale, where you apply a voltage and you can modify either the refractive index or the polarization of a light pulse, and you can reroute that pulse then in a variety of ways. They've developed a birefringence compensated Pockle cell that can run at very high average powers. Adaptive optics for closed loop control, and then they've also developed new media for frequency conversion, also at rep rate. So all of these are really pushing 100 joules at 10 hertz in a manner that can be scalable. So if we could take that 100 joule 10 hertz laser and then scale it up, we would have sort of the architecture that's required to build a power plant. So that's sort of our artist rendition of what the power plant might look like. We have a concept called LIFE, or laser inertial fusion energy. And it really has 2 applications. One of them is for clean, pure fusion, in which we take these lasers and we get more energy out than we put in, and then put that power on the grid. Another application, which is sort of a hybrid, is we have a fission-fusion reaction, in which we surround the target chamber with partially spent nuclear fuel, and we use the neutrons that come out of the fusion reaction, not necessarily for producing energy, but for accelerating the fission and further breakdown of that nuclear waste. So as a benefit, we would take waste that's been stored from fission plants that's no longer economically viable to burn down to 0, and we'd be able to burn it up. We're sort of targeting a prototype plant in the 2025 time frame, but we have a number of challenges that we need to meet before we get there. So I think I'm on time. In summary, at NIF, we're sort of pursuing the frontiers of laser energy and peak power. By the end of this year, we hope to have the first demonstration of ignition. We completed the laser last year, and right now we're getting the laser ready so that we can operate it reliably for the next 30 years. And we're going to have a radioactive environment soon, so we're making sure that we get all the infrastructure in there now before it becomes very difficult to service. But hopefully by the end of this year, we'll have the first demonstration of gain. Let's see. So a lot of the NIF has been made possible really by scaling up the aperture of the gain media, the purity of the optics, and creating a very adaptable front-end injection laser system, which can deal with damaged sites, which can tailor the pulses and tweak the parameters required to achieve this careful balance. In the next few years, we'll have these petawatt beams installed, and then our next goal will be to look towards, how do we really make this into a power plant? How do we solve the rep rate problem? How do we extract energy thermally from the media? How do we make the targets cheap? How do we get the diode lasers down cheap? And then how do we make this really always on demand so that we can fire this thing continuously? So thank you for your time.
Thank you, John. Again, there's time for questions. Please identify yourself and your institution.
Is it on? Oh, thank you. This is Poyan Porbek, Electric Power Research Institute. On the power plant application, 2 questions. One, what is the energy conversion mechanism you're using at the end? How are you extracting or proposing to extract the heat? Is it just create steam into a steam turbine?
Yeah, ultimately, it's you would trap the neutrons. The neutrons capture have most of the kinetic energy from the reaction. You would use standard materials from the fission industry to trap those neutrons, convert them to heat, flow coolant around them, and then in a secondary exchange, convert that heat over into water and then run a conventional turbine. But there's various proposals at this stage. Okay. That's sort of your canonical
And what kind of efficiency do you think is achievable from this system?
Yeah, so right now the designers are saying that we'll be running with something like it's 300 to 500 megajoules per shot at 15 hertz. So that takes you up to well into the gigawatts with consumption of power just under a gigawatt. So we're talking about aiming at net energy or net powers on average of about 500 megawatts to a gigawatt, somewhere in that ballpark. So it depends on how you define it. Oh, I see. Yep. Yeah, so I think that's going to be of the order of similar, 25% perhaps. Yep. Of that order. Yep.
Klaus Daniel, Oak Ridge National Laboratory. It's a very intriguing idea of creating fusion with the laser. Are you having any relationship, or are you following, or are you in competition with the ITER project in France, or how is that? How do you see that relationship there?
Sure. The ITER project in France is a parallel approach that has been going back to the tokamak in the Soviet Union as well as in Princeton and other locations. And there, the goal was to try to achieve very high energy densities for very long time frames and operate these this magnetic confinement continuously. ITER is, I believe, on schedule to complete and get ignition equivalent in 2025 or 2026 at this point. ICF started later, as inertial confinement fusion with lasers, started later. It's had a number of breakthroughs that have allowed us to get to where we need to be faster than the magnetic approach. So hopefully this year we'll be able to achieve ignition. The real question is going forward, can we make this viable at high rep rates? We have to inject targets at 15 hertz. We have to track those targets and detonate them, much like an automobile engine. So there's a lot of challenges there. But the two approaches are at some level in competition, but there's a lot of uncertainty as to which one's going to win out at this point.
It seems to be much more feasible from the point of view of size and potentially cost. Do I have a wrong understanding?
Which one?
With yours.
I think a lot of these questions really are unknown at this point. I mean, there's very biased opinions on both sides, of course. But yeah.
Madhu Raghavan from General Motors R&D. On your timeline, you had the Life fusion engine coming on at 2020. So what else needs to happen between now and then?
Okay, so Yes, we need to be able to leverage the technologies that were developed for the Mercury Laser and design an architecture that's compact and cost-effective so that we can build this power plant on a reasonable time frame. We have to leverage advances made for military-class lasers for tracking missiles. That is, the angular sweep rates for tracking, say, that Boeing uses are almost directly applicable here to track targets, because you're going to be injecting these targets with mechanical jitter, and we need to synchronize these pulses sort of at the few picosecond time scale. So, in addition, there's some economic drivers that need to happen. We need to figure out how to make these targets cheap. We need to make them assembly line style, and we need to figure out how to bring down the cost of diodes working with industrial partners, because NIF is powered, I didn't mention this, by flash lamps, sort of old laser technology. We need to be able to operate these with diodes, which are very efficient at converting electrical energy into laser pump energy, and then, which is very spatially incoherent. And then we use our gain media to convert that massive array of diodes, which at this point are projected to cost something like $500 million just to build this plant, just the diodes.
This is Judy from University of Pennsylvania. My question is, are you using commercial power grid to pump the lasers?
Yeah, for NIF, we're essentially charging capacitors off of the commercial grid.
And did Enron, when the California electric grid, put some burden on your budget of powering?
No, I mean, the actual energy consumption is quite small. One way to think about it is 1 megajoule of optical energy is equivalent to 1 jelly donut of chemical energy. So we always like to, actually characterize these high-energy lasers in terms of the number of jelly donuts. But in terms of kilowatt hours, it's of the order of unity. It's only a few kilowatt hours that we need to charge these capacitors to for a single shot. It's the pulse width that's really small and the high peak powers, the energy delivered in a short burst of time that characterizes these systems.
So Hui Tao from Yale University. So how did you get rid of the speckle by destroy the coherence?
Oh, okay. For a number of ways. You can generate speckle in these systems simply because the beams want to break up and filament due to Kerr lensing, nonlinear focusing processes. So for that, we need spatial filters at multiple points in the chain. But by the time you get to the final interaction of all the beams on the target, you have this coherent addition of fields that you want to try to spoil. And so one of the ways we do it is we put a phase plate in. And you can think of this phase plate like shower glass, although it's more deterministically controlled. And in addition to that, we dither the wavelength. That is, we FM, or frequency modulate, the pulse at the front end. We bounce that off of a diffraction grating so that the far field spot, or the pointed spot, actually shifts many times within a nanosecond. So it's about 17 gigahertz. So you have 17 oscillations within a nanosecond for all of these beams, in addition to this phase plate, in addition to heating up this gold holerum and ejecting incoherent X-rays. If you add those all up together, you end up with a very smooth, symmetrical blackbody oven of X-rays.
Dirk Westermann, Livermore University of Technology. My question was, do you have any idea on the size of such a power plant? Because I think it could be enormous in terms of space requirements in order to produce 1 gigawatt, say, or 2 gigawatts of electricity.
Yeah, so NIF right now is, let's see, this is about 200 meters by 130 meters. And the life plants that we're working on right now are about half that size. So we hope to, if we pursue the fusion-fission approach, we hope to co-locate this with a repository of spent nuclear fuel. Repositories of spent nuclear fuel tend to be in areas that are very unpopulated, very expansive. So yes, we have a strong drive to try to make this as compact as possible. But at the same time, we envision that the early power plants will be deployed in non-residential areas.
Gabi Pradl, University of Würzburg. I was wondering, how many people do you need to maintain and operate a NIF laser?
So over the last little over 10 years, well over 1,000 people contributed to building the project, but a lot of people have come and gone. At our lab, people work on various projects, much like at this lab, and they contribute something and move on. So scientists first design the architectures, engineers come along, technicians come along, and get to the production phase. As far as operating NIF day to day, I think we have probably something like 70 people in a control room, as well as getting ready to maintain and deal with emergency situations, something of that order.
Andreas Malikopoulos, General Motors Research and Development. I was wondering, how do you come up with these pulse width profiles that you've shown earlier on? Do you use any particular optimization methods for this one?
Yes. Sort of that's the purview of the plasma physicists and the nuclear physicists that get to play all day long on the supercomputers. So they have 1D through 3D codes that model plasma magnetohydrodynamics and shock physics. And there's many competing designs, and a lot of them still need to be validated. But those individual features that you see there on the foot or the leading edge of the pulse have all been at some level already validated on NIF, as well as on smaller scale systems. So there's a lot of consensus that this is the right approach. The actual details of where those pulses are going to be in time, what their amplitudes are going to be, is still a matter of, we're going to tweak those over the next few years, perhaps for a long time.
One other question. This is Poyan again. Imminently, the second option is the more attractive from the power industry perspective, because you've got, the biggest issue on the nuclear side is the spent fuel storage. Mm-hmm. Despite what general public might think, the fission reaction is very reliable. Despite Chernobyl and 3 Mile Island, these events don't happen. It's how do you store all that nuclear fuel that's the big controversy. So if you could make that work, that would be fabulous. The question is there any limit on, does the fuel have to be at a certain radioactive level to be applicable to this? And secondly, if you did it in this technique, can you really spend it to basically, default background radiation, just disperse it anywhere, or no?
Well, our nuclear physicists have been working on this problem. Have been modeling it from the level of triso fuel pellets that are standard in the fission industry, and filling these pellets into a thin, sort of annular region of a spherical shell, target chamber. And as far as spending that fuel down, I think it's something like a 5-year cycle in which you would cycle these pellets through, and they would recycle their way out, and then at some level they're spent, and you can process them as lead. But these two approaches are being pursued right now because it's not clear certainly which is the one that's going to attract the funding to be able to build this plant. So we're keeping those two options open. Certainly the pure fusion approach is something that's been a dream of Livermore's and others for quite some time. If this takes off first, then we're not going to complain.
Klerk Machi, Princeton. I wondered why are you going to the third harmonic? If you're just compressing mechanically a target, you could do that probably with a lower harmonic and not lose efficiency as you upconvert the beam.
Sure. So there's an efficiency loss in converting the optical photons from IR to the green to the ultraviolet. But then there are other inefficiencies that creep in when these beams interact in the gold cylinder in the whole room that really are nonlinear optical interactions in the plasma. And you have stimulated Raman scattering, you have stimulated Brillouin scattering, and you also have the conversion, the efficiency of conversion from X-ray, from UV to the X-rays. And there is still a little bit of debate as to whether or not green versus ultraviolet is better. But if you go through all the numbers and you cascade all the efficiencies, the IR is not the way to go. So right now the baseline is ultraviolet, but there are still some experimenters that would like us to see green experiments done. And we can actually do that by tuning the wavelength off of the converter crystal.
Last question.
Duncan Calloway, UC Berkeley, and it's actually just following on to what you were asking about, and an earlier question about the efficiency of the overall system. Do you have a sense of how much of the efficiency loss in an ultimate fusion facility would be just due to the creation of the light source? So how many losses are there in your sort of optical side of things?
Sure. So NIF right now is less than 1% efficient. And that's mainly because of the gain media we're using and the pump source using flash lamps. Flash lamps emit very broad band spectrum, and not all of that gets absorbed into the gain media. For a life power plant pumped by very monochromatic diode lasers that are really pumping absorption bands that are very narrow as well, the efficiency comes down to the quantum defect of the material as well as the efficiency of the diode lasers themselves. So going from well under 1% to just 30% would be a huge improvement. And then you have to counterbalance that against the fact that we're injecting deuterium and tritium, which are going to require a lot of economic investment to bring the cost down. But still, there's an enormous amount of energy contained in that deuterium tritium if we can only extract it. So the gain of the final process makes up for a lot of that inefficiency, in which we would inject just a few megajoules of light, and we would extract hundreds of megajoules of neutron kinetic energy.
Thank you all for your questions, and let's thank John for his talk and answers.